In this session, we'll finish up our last three continuous distribution families. The first family of distribution is called student T distribution, or the T distribution. The T distribution is very closely related to the standard normal distribution. Recall that the standard normal distribution, the mean is 0 and the standard deviation was 1. Okay. Here in T distribution, the standard deviation is nu over nu minus 2, where nu is the degree of freedom. The degree of freedom. Now, this is just a generalized term. What we do replace nu with in terms of applications is frequently we set it to the sample size n minus 1. So n minus 1 will be the calculation. So when we perform sampling with the measurements drawn from a normal distribution, but we are not aware of the population standard deviation. Something we'll discuss a lot more in lesson 4, right? So in sampling situations where we do have the sample size n, let's say n is 16, then our degree of freedom is 16 minus 1. So that's 15. And so our standard deviation will be 15 over 15 minus 2. And so that's 15 over 13. That's slightly more than 1. So it's larger fluctuations than the equivalent standard normal. Standard normal is always 0. SD is always 1. So you can see from the formula here that the standard deviation is kind of always larger than 1. And it gets smaller and smaller and closer to 1 as nu, the degree of freedom, increases towards infinity. So we can see that one plot with a small nu, a small degree of freedom, 2 or 3, will look like this. When we have a lot of T distributions going from the green one being nu equals to 1, followed by 2, followed by 4, 8, 16, and then we have, by the time it's 16, it's almost indistinguishable from the standard normal, which is the outermost, topmost line, if you can see in the middle here, all right, and the bottommost line after this crossing. So it's symmetrical about 0, and the standard normal distribution centered at 0 all the time is the sort of envelope around the whole family of infinitely many T distributions. So that is from the picture. And of course, when they are kind of related graphically, we get a sense that they somehow T and Z must be related. And you're right. So as the degree of freedom, as nu increases towards infinity, then T distribution becomes exactly the same as normal, standard normal distribution. Not all other normals, but standard normal, because the mean has to be 0 and the sigma is 1, as we'll see, right? As nu goes to infinity, it's like 1 million over 1 million minus 2. So it's basically 1. So we at least from the standard deviation perspective, we see that it is, already very closing in. And it is indeed true that when nu increases to infinity, T becomes standard normal. Why do we need this? Okay, it's all theoretical, right? So just to be more technically correct, statisticians and scientists invented this T distribution so that in the situations when we know or we assume that the measurements are drawn from a normal distribution, something which is reasonable, even if you don't know exactly it is normal, it is quite okay, acceptable to assume that the measurements come from a normal distribution. What is less acceptable is that oftentimes we don't know the population standard deviation. And to assume that we know the population standard deviation, and yet we don't know the population mean, is a little bit problematic logically, because as we knew in the variance calculations, that variance calculation involves knowing the population mean. So how can we know the variance when we claim that we don't know the population mean? You see, there's a little bit of a logical trap there, and it's dangerous to ignore this problem. And that's why we have to rely on t-distribution, where t-distribution was created by design, so it's artificially created, with the understanding that we don't know the population standard deviation. Okay? And we are going to approximate that using sample standard deviation. So now that might seem like, well, you just change a word, right? No, it's not so simple, because sample anything, sample mean, sample standard deviation, sample whatever, can always be absolutely calculated. They are always close, but not exactly the same as population mean, population standard deviation, and so on. So therefore, when we perform certain statistical calculations, it is important to kind of take into account, yeah, the lack of knowledge of the population standard deviation and the injected uncertainty when we use the sample standard deviation as if it were the population standard deviation. You see that? So this is the crucial part of it. And because of this correction, if you want to put it that way, we have to use the student t distribution whenever we are in this situation. And this situation comes in every time we perform sampling. And statistics is no longer statistics if we don't do sampling, right? So, and we don't do measurements, and we don't do collection of data through limited resources. So this becomes a must almost for every statistical calculations that we come across in real life. So that's why t distribution, as artificial and fabricated as it is part and parcel of all statistical computations. Okay, so just keep that in mind, and we'll see that again. Chi-square and F distributions. Very useful distributions in subsequent discussions in establishing confidence intervals for the variance. If you're asking, hey, when you do these measurements of the height of students in the universities, what about, can you give me a range, like a plus minus of the variance? How varying are these students in terms of the variance? The range of the variance, right? So the variation of the variance. So when we ask questions like that, we have to talk about chi-square distribution. When we perform sum of the squares of normal distributions, we have to talk about chi-square distributions. So chi-square distributions are very useful distributions in that sense, and they will come in with the chi-square tests, something we'll discuss later on in lecture 8 and others. And just to kind of give a picture of, you can think of it as a bell curve squared plus bell curve squared plus bell curve squared, and so on, gives rise to, I won't actually say equal to, but gives rise to chi-square. Can we do that? Okay. So if you have this, then the degree of freedom is 2, because there are 2 curves that we use in the chi-square in arriving at the chi-square. All right, so if you add them together, you will get chi-square. Chi-square will be will look rather strange, will look not like bell curve at all. And it starts from 0. All right, remember our normal distribution is from minus infinity to infinity. When you square it, it's going from 0 to infinity. And then you sum them together, you will get 0 to infinity, but in a curve that is looking rather non-normal like this. Okay, so that's one example of chi-square. It will always look like that, like one lump on the left side and then sort of curves never-endingly towards infinity. What's the mean? It's nu itself. So higher the degree of freedom, the more normal squares that you add, the larger the mean. Kind of makes sense. The variance varies with the mean. You see? So in fact, it's twice the mean. So the more chi-square, sorry, the more normal square you add to form a chi-square, the greater, more magnified is the variance. So in practical purposes, we don't want to really use too many normal squares added together, because your variance is going to be so large that the result is not very clear. It can be from here, it can be from there, and it's less certain about the answers. So normally we also don't want to pile on too many. That means we don't want to make the degree of freedom too large. So a pictorial way to show this chi-square hopefully will then, ground you to the floor and not start to think about chi-square as something floating down from alien world, but it's really again another construction, another fabrication in mathematics, resulting from summing the squares of normal distributions. And the last class of continuous distribution we like to just touch on and explore later in lectures 8 and 9, and that's called the F distribution. All right, so Fisher-Snedecor distribution is a class of distributions that requires two parameters. We call it the numerator degree of freedom, and nu2 is the denominator degree of freedom. And that sounds a little bit strange until you allow me to again draw a picture quickly to show you what do you mean by numerator and denominator. And the whole idea is it is like having two chi-squares, one chi-square divided by another chi-square distribution gives rise to F distribution, right? So F distribution can be like that, can take many forms. So one chi-square distribution divided by another chi-square distribution gives rise to an F distribution. Now that is more like a storytelling. In general, that's the design of F distribution. Of course, how to divide and how do you arrive at this PDF for F distribution? That's just way too complicated. But it is sufficient and very beneficial to know the origins of F distribution. It's not something that's landed from nowhere. It's kind of a fabrication created to address a need, and that is one is for the ratio of chi-square distributions. Whenever we have to divide chi-square distributions, then what do we do? And remember what is chi-square? Chi-square is sum of a number of square of normal distributions. Okay, and also when we have two population variance tests, something we talk a lot more about in lectures 8 and 9. And when we perform two population variance tests, we also have other tests, such as the ANOVA test, which is very useful and maybe even famous. And all these tests require us to perform some sort of a ratio. Which variance is larger? Is this variance, is this chi-square larger, or that variance, that chi-square is larger? So we need to do some sort of a ratio. Is it larger than 1 or lesser than 1? When we do that division, distribution divided by distribution, and we can do that. You just have to be mathematically, careful. And if you do that, then you will end up having the need to have a well-known class of distributions as a result of dividing chi-square by chi-square. And that answer is F distribution. All right. So where do we use them? Two population variance tests. ANOVA test. Linear regression, right, which involves ANOVA, which therefore involves F distribution. So this distribution, super complicated. We don't have to worry about the complicated part of it, but super useful because a lot of the interesting things come from all these tests. All right, so we will get to see a lot more details in lessons 8 and 9. So stay with me and see you there.